input for water productivity. So we are moving towards smart irrigation and from micro irrigation. And this smart irrigation uses sensors and data, automatic data related to weather, soil, for automatically scheduling the water and estimating the correct amount of water for irrigation. So in this first webinar lecture, we have a speaker, Mr. Kowshik from Medha-Rubicon, who will be delivering the talk. But before that, I will request our president, Dr. Marco Arcieri, to say a few words about this topic. Yes. President, Dr. Marco Arcieri.
I'm sorry, I cannot be more actively involved in this very interesting seminar and webinar, which actually is focused on one of the most interesting arguments I feel that we should be focusing on in these days, because, as you know, I'm very very sensitive, very keen for especially for irrigation scheduling, which is one of the I think one of the new frontiers for having smart irrigation management, and especially in order to save water. I'm on the train. Actually, I have been attending the Italian National Committee of I Cold conference in Milan, close to Milan. So today I'm coming
President, there is some issue with the signal. Your voice is not so clear.
Oh.
Yeah. Your voice is not coming, President.
Pakistan, and then from there we'll go to Japan, and from there to China, and so on. So I am sure.
Okay, President, shall we start the presentation now?
Hello.
Yeah, we cannot hear you now.
Can you hear me now?
Yes, now we can hear you. Not now.
Yes, can you hear me now? Can you hear me?
Yes.
Okay. Okay, start presentation. Okay. No, I will.
Okay, thank you, President. Before I request Mr. Kowshik to give the presentation, I will request all participants, if they have any question, they can write their question, name, and email in the chat box. And I will ask Mr. Kowshik to answer as many as possible. And if not today, then later on after the presentation, he should try to answer all the questions. So, so Mr. Kowshik is working with Messrs. Medha-Rubicon for quite a long time, and he is an expert now in Smart Irrigation Management. So now I will request Mr. Kowshik to give the presentation.
Thank you.
Thank you. Screen. Um, Hope my screen is visible, sir.
Yes, your presentation is visible. Make it full screen.
Please let me know when you can see my full screen, sir.
I'm not seeing your presentation right now.
Okay, 1 minute. Hope this is visible now.
Yes, yes.
Yeah, okay, okay. Thanks for confirming, sir. So, to begin with, greetings of the day to the President ICID, Dr. Marco Arcieri. Really appreciate his dedication and to attend the presentation and seminar and webinar and make it begin. And I'm thankful to Dr. R.K. Gupta ji, Secretary General ICID, respected staff members, and the curious participants. Thank you so much for being here. I'm also very thankful to the chair for facilitating this platform to share the views on the technology straight from the industries. A really smart, move to bring everything or share knowledge at a global level. Uh, and a brief introduction of about myself. I'm Kowshik, and I have been working with Medha-Rubicon for quite a time. And as sir said, I have been in the projects of implementing irrigation and smart irrigation projects since 2019. And I have had the privilege to be a part from the very scratch of the project's commencement, which gives me, the ground reality of the existing scenarios in the field. During this period of half a decade's journey, I have collected ground realities and informations straight from the field, and I hope I'll be able to justify the agenda I have prepared, which will be going through the introduction of what exactly we are going to talk about, and going forward the challenges which we are going to face, which are there in the irrigation networks, uh, followed by the technological interventions which are able to provide or solution to the existing problems, and the smart infrastructure that is put into the play so that this challenges can be mitigated. At the same time, to support the whole concept, I would like to put forward to you a case study on KBJNL NLBC SCADA Phase 2 project, which has proven itself not just on the paper but physically witnessed by the farmers themselves, who are the stakeholders at the end of the day. Finally, we will be talking about few more implementations across India, and I will brief and comment myself towards what Medha Servo Tribes is and what Rubicon Water is at the end of the discussion. Going forward, let me introduce like what the topic which we are going to talk about today under the theme of smart irrigation management. Water is a very necessary resource which has to be, which is needed by every life on earth. Coming back to the requirement of the humans, fresh water becomes the very major source to a wide variety of sectors, including industries, manufacturing, and at the same time, the food production. The food production requires the fresh water, and it is mainly coming from the groundwater or from the water which is there on the surface. According to the water management survey, which was conducted by USDA. It was published that around 45% of water which is available on the ground is applied for irrigation, and that came from the surface water, and the remaining obtained is from the groundwater resources. It could be tube well or hand pumps or like that. A conducted survey of 2030 strongly feels that there is a deficit of fresh water up to 40% in the upcoming years of 2030, where the requirement of fresh water is rapidly increasing with the increasing population, and we will reach a stage where there will be a deficit of 40% of fresh water that is required. This fresh water again accounts to 70% of the global water which is required for the irrigation or agricultural practices. So agriculture requires around 70% of the global fresh water. Indirectly, we can consider water as currency or the currency of life. Uh, and coming back to the canal-based irrigation systems, these systems where there are perennial rivers or there is a requirement of water distant from the sources of the main catchment. These canal-based irrigation methodology plays a pivotal role. And this contributes to around 24% of the total irrigation done in India, which is a very massive chunk. Now, going to the challenges which we will be having. When we talk about canal systems, we are very clear about few things, that either it could be lift irrigation or it could be a canal passing from a dam. In either of the places, we have a reservoir from which the canals are, drawn out. And the best practice, best or common practice that is implemented is for the gravity-fed irrigation, or the water flows by the gravity from the dam to the tail-end farmers. Here, many questions arise with the time. The first question being, how much water a farmer is expecting, whether the water is reaching the tail till the requirement of the farmer is completed, who is having a crop which is growing based on the water requirement, which is requested by him for the existing crop. Going forward, how much is the effectiveness of the canal control, and actually how much water is there in the dam, and is it able to fulfill the requirement of the farmer's irrigation till the end of the cropping season, or till the crop requires the water. And hence there is a requirement of what is a management, or how the planning is done by the main authorities who are having control over the dam. Going forward, what are the main challenges to the delivery efficiency? Let me put a small definition before we go forward, like what delivery efficiency means. Delivery efficiency of a canal is nothing but conveyance efficiency, which is the ratio between how much water which has reached the field or has been delivered against the water which was actually released for the purpose, that is from the source or from the reservoir. You can see in the picture that there are different losses that can happen towards the journey of the conveyance of water, which could be evaporation, which could be leakages, which could be spills, and some leakages around the structures. But how much do you think is contributing to these losses? Let us say 10%, 15%, or let us say a maximum of 30%. But what about the remaining 70% of the water which is supposed to conveyed to the end feed? There, the following challenges come into play. The first challenge in such scenarios is damaged or not working gates, non-working gates. Here, these gates, when are not working, are unable to give the correct measurement or correct amount of water into the canal, into the required channel. Challenge number two is due to the manual operations. This is a conventional practice in majority of the regions across the world, wherein the gates are operated, structures are operated manually by intervening with the existing structure, going there, rotating with the help of a manual lever, and then getting the water released to the right channel. It has been an efficient practice till the date, but it has a huge drawbacks to itself, where the delays in manual operations can cause significant losses to the conveyance or the time at which the crop actually requires water. The third challenge is waterlogging and no moisture data. Now, there are two phases to a coin in similar way. There is ativrishti, anavrishti, we call in Sanskrit, where excess water or deficiency of water are both very critical and very dangerous to the crop or the produce. Here, waterlogging is a major practice, major disaster that can happen to any crop, and there is a proper planning that has to be done in order to save crops from waterlogging. And if there were any soil moisture data, it could have been, mitigated in the earlier stages itself. The fourth challenge is the limited workforce versus the command area. My audience, I believe, are very enthusiasts in the canal sector. At the same time, I believe that they have a good sense of understanding that the canal that we serve uh, water through has a vast command area to serve usually. The canals range up to 3,000, 4,000 kilometers. At the same time, the workforce which we have is quite limited, and it becomes a very challenging aspect to manage the water till the tail end of the vicinity of the command area. And the final challenge is the lack of safety and flood management. Most of the cases where if you can get the alarms of the inflow or the outflow, which is coming into the catchment area till the dam, and from the water which is drawn by the canal, there could be a significant amount of savings in terms of life and resources. Now we have talked about challenges. Now we will talk about how technological intervention is believed to help in this particular scenarios. The technological intervention we will be talking about will be from the dam to the crop scenario, where the starting stage will be from the monitoring, catchment, big data, and till the dam control. This is where the monitoring part plays a role, like how much water is coming through, how much water do you have in the canal, how much you in the dam, in the dam, and how much you are going to, let go to the bottom or let go to the downstream of the canals so that it serves the purposes. Second one is managing the water which is released. Once the water is released from the dam, it has to be distributed efficiently within the district of water resources, so that each and every beneficiary is getting his equitable share of water. Finally, last but not the least, which is a major part of it, is to deliver the water to the stakeholders or the end users. That is happening with the efficient management and monitoring of the data which is there in the dam, followed by the channels, and finally till the tail end, where the farmer who or the irrigator is quite aware like how much water is required and how much water is to be drawn from the canal. Now, generic data says that the current efficiency of open channel canals uh, is ranging up to just above or 30 to 40%, but the actual target that can be achieved can be 80% with the right resources, with the right technological interventions. And the data also emphasizes on the fact that less than 44% of the water released in the dam is actually required by the crop, which means the remaining 56% of the water is either delivered for the purpose of the creation of head or to creation of the flow to the downstream, or just goes unaccounted due to certain uncontrollable scenarios where the gate structures are not in control. Now, this 80% and above can be reached with the help of three different methodology. The first one, distributing the water to the specific canal, specific source with the right measurement and scheduling, in which there is a precise calculation like how much water is required at what period of time, where the farmer or irrigator is well educated. At the same time, the cropping pattern is regulated. At the same time, how much water is there in the catchment area is also equally understood. And the final stage is application, where the precision control comes into play. It could be drip, it could be sprinkler, or it could be just a precise gate measuring the water which is flowing through the channel. Going forward, let me summarize the whole thing which I just discussed. Like in the previous picture, we could just see the questions. Let me try to put the answers to them. The first one being how much water is in the dam. How can it be calculated? How can it be mitigated? With the help of a real-time level monitoring and gate control. The second question was, what is the effectiveness of the control? Now, this effectiveness can be put into accountability with the help of autonomous gates, which are operating on their own with the help of the command, which is given from the irrigation management softwares. That is where the water release management and planning takes place. Now we have this vast command area. What should be done? So we have the solution as the remote operation could be one way where the existing force can be used. And finally, how do you know that how much water is there, how much water has reached the end of the canal? That is a feedback from the tail end could be helpful. And what is the farmer doing? He is intelligently now can be planning the whole schedule based on the availability of water. Had he had information in his hand like how much water is available and for how long he'll be getting it. Going to the solution part of it now, how the smart infrastructures can be put in the right places where we just thought the thought process into this particular channel. There's a small graphics over here. I hope you can all see this particular thing where the upstream water has fluctuations, whereas the downstream itself is again fluctuating up and down in order to maintain the mean line that is red in color here. And you can see the fluctuations. Fluctuations are not only disturbing the whole fact of giving how much water is there, how much water is going through the canal. At the same time, it is also causing disturbances which are susceptible to, have some effect to the infrastructure itself. When I say infrastructure, it could be canal lining or the structures in between or piers with the canal. Now let us see this particular operation where you can see the automated delivery. As you can see that the upstream and downstream is increasing or decreasing, the gate is adjusting on its own to maintain the level of the water in the downstream, and the water remains at the mean level, very meager fluctuations, and thus creating a very smooth curve of water flow, maintaining the downstream level which is intended at the end of the day. Now, automated delivery and remote control comes with uh, the technological part of it, like what are the points that are to be introduced, weather stations at the endpoints, energy efficient structures where you require the least amount of energy to be contributed, ag tech apps which are related to monitoring of the agricultural practices which are going on in the field. Monitoring stations could be a good example for that. Remote irrigation management, where you can uh, use the applications, to identify how much water has to be released at what time. Water accounting becomes a very important factor where water can be measured and precisely applied to the irrigator or the person who is benefiting. And finally, the main metering device. How much water is required can be metered along with the controllable structures which are controlling the flow of the water through them. The basic solution which is being implemented, which can be implemented, are with the help of the gates at the outlets. The conventional gates being heavy at the same time, operational on a manual operation level. The same thing can be replaced with the autonomous gates. What are the advantages of these autonomous gates when we talk about? These gates will be having modular designs which are easy to install and has minimal change in the design that is required in the existing canals. These gates can be coming in varied sizes, get standardized with the parts which are being used, so that in case there is a requirement of changing parts, they do not take much time of their own. Going forward, watertight seals should be there. At the same time, the gates come with aluminum alloy castings, and which are corrosion resistant, which do not get affected with the water quality available in that region. Again, the gates, have their SCADA connectivity and are solar panel operated. These gates can be, position mode and flow mode can be used for these, where the position mode will simply give you at what percentage of opening of the gate or the vent has been determined, or and the flow mode will give you how much flow has to be passed through the vent which is available over there. And these smart gates have the transducers in them, which are capable of monitoring the flow with an accuracy of plus or minus 2.5%, which is a very phenomenal accountability of water which is flowing through the channel and still controlling the flow of it. This is an autonomous overshot gate. When we say overshot, the gates are letting the water flow from the top, as you can see in the animation. The conventional gates and the cross regulators operate at the levels of undershot gates, where the water usually flows from the bottom. Flows from the bottom, when I say that a gate opening happens towards the upward direction and there is a channel opening created at the bottom. But these overshot gates will bring us with the precise calculation of water which is going through them, controlling the upstream and the downstream water level by measuring continuously and operating on their own. The salient features of such gates are that they are integrated with upstream and downstream level sensors. They have an accuracy of plus or minus 2.5% integrated flow measurement. and the precision of the gate can range up to plus or minus 0.1 mm, which will help us to maintain the head to a very good extent. Head, when I say, is the amount of water that is raising in the upstream. And again, the quality of the material is again marine grade aluminum alloy, which is certified across the major laboratories in Australia and India. The SCADA connectivity for remote operations and the coordination with other gates is also possible with this smart gate, where each gate comes with its own pedestal that has the capacity to talk to each and every gate independently via radio communication or GSM facility. All these gates also come with solar powered battery that is having a lifetime of 72 hours with a continuous operation. When I say 72 hours, this operation is for 3 continuous days where the sun did not shine for the solar power. At the same time, they have been operating to at least once in 10 minutes to maintain itself and communicate its measurement and the flow with the main control server. Again, this particular gate also comes with two modes of control, that is position mode and flow mode. And finally, it is quite rigid at the same time lightweight. So this particular gate acts as a adjustable wear, which conventionally used to be a temporary or permanent or rigid wear kind of thing. And now this leaf can be adjusted up and down as per the requirement to maintain the head at the upstream and also the flow at the downstream of it. The integrated communication under uh, this particular solution will be acting in such a fashion that each gate will be talking to a tower which is available, which is usually called a node. Now, a gate can be operated from the control center in such a way that the signals go to the towers, tower distribute them to the respective gate. Each gate again talks to a tower, and the gate is also capable of talking to another gate, requesting or asking the confirmations of the water level availability. In case of failure of one particular node, also there is a significant uh, channelization where each gate can talk to each other, and the information is finally passed on to the central command center, which is control center, and each parameter is noted and monitored from there, and at the same time uh, can be controlling the remote devices. Now, how about software? Now, this is the critical part of it, where irrigation management software comes into play. The irrigation management software has to have the capability to operate and control multiple nodes all at the same time. At the same time, should be able to visualize and analyze the data which is going and coming from the canal. This is an example screens which have been put here where the network is visualized. The network overview can be seen. This is a dashboard where you can see the status of the gates which are happening, which are available in the theme, and an analysis of what happened in the history or the past based on which decision making can take place. And obviously, with the technology at hand, we are capable enough to, monitor the gates from a remote location, as accessible to the farmer who is in the field from a mobile application, where orders, rotations, and scheduling should be an integral part of the irrigation management software. Finally, the tail end sensors, which are the weather stations. The weather stations should be capable or are capable of measuring the rainfall, the temperature, the humidity, the wind speed, the solar radiation, and atmospheric pressure. So these are sophisticated systems which is like uh, 130 centimeters high structure, which can be mounted on a simple gate. And it has a low maintenance and unique design where so many parameters starting from precipitation collector, pyranometer for the solar radiation, ultrasonic level sensors, and automatic rapid release valves and anemometer is also there, including the inclinometer and compass in it. Not last but not the least, these devices come up with soil moisture probe, where the moisture in the soil is collected and then sent to the main server for the effective decision making, and based on which the the manager is able to decide if the water is actually required by the recipient or not. Now, let us see how all these devices, when put together, will be working here. Now, when we last talked was about the sensors data, which is coming directly from the field. And once the data is there, the data from the sensors and weather sources are required and collected, and the signals from this are reaching to the farmer who is holding a farm and is ready to have his water for application. Now he is raising a demand from the for the water, and the demand has now requested the head office of the irrigation department, where the water demand request is validated, whether the farmer is, you know, uh, actually the requirement is genuine, or like whether he has to be allocated, how much is to be allocated, and that decision or analysis or scheduling is done by the water authority with the help of the software or allocation applications. Now, once it is verified, the same thing is sent as instructions to the gates, and that is done via the communication network. These communication networks are then talking to the tail end, that is to release the water to the field channels. Once the water is released to the field channel, the the gate is talking to the previous gate saying that, okay, I have received so much water, release instruction. Now what shall happen to the water release? So it is going to talk to the up next gate, talking about the feedback, that there is a pool, contiguous pool, that is to be maintained. When I say contiguous pools, you can see the small structures here. These are the cross regulators where they are maintaining the pools from the upstream and downstream. Now, in order to fulfill the pool which has been taken up or benefited by the farmers, the same thing is sent to the dam structure. The dam now has the idea like how much water is to be released, so that the actual water which is consumed is replenished and the structures are efficient enough to have the next water release by the next request. So let us see how the whole thing has been implemented in KB General SCADA Phase 2 project, which was under the flagship or initiative of PMKSY by the central government, and with the help of the organization or KB General Krishna Bhagya Jala Nigam Limited in the Narayanpur left bank canal, that is in Karnataka. Now, the primary objective here again was to increase the operational efficiency. That is, with the water metered at the farm outlets, like how much was there. The current, it was told to be 60%, and it was supposed to be, increasing up to 80% and more, in turn making the water available for the productive uses. The second main primary objective was to transparent water supply, where there was a requirement of accounting how much water is going to which canal and which outlet, so that the accountability takes place. and the actual deficit or actual remaining water can be used for other projects, as well as to be released into the main main river source. And near on-demand water supply was another objective for the project to accomplish, where the water has to be reaching the farmer within the period of time allocated to him. And last but not the least, which was flexible and reliable water supply even during the Varabandi period, where the water release is stopped to a weeks period and then released into the canal at certain intervals. The project scope included the 450 gates, that is for the field channel outlet gates, which were around 3,685 numbers. The offtake or lateral gates, which were around 518 numbers, and the existing cross regulators in the system back established in 1970s or 80s were 144, and there were water level sensors which were to be integrated with the existing cross regulators, 43 numbers. RTU rooms to have the electronics of the existing cross regulators collected. There were 41 numbers, 41 locations were there. And along with that, for the monitoring purpose, 42 monitoring stations were provided. New cross regulators were also in the scope, where the existing canal had to be completely excavated and had to produce have to be introduced with new cross regulators, where the submergence becomes a problem. The contiguous pools was the intention. Those new cross regulators were introduced, and around 15 numbers of radio communication towers were established for the vast command area of 408,000 hectares of the command area of KVJ and NLBC. One command center in the same building of the department was allocated, and from which the operations are taken care till date. 33 open channel flow meters were there, where for the purpose of measuring flow at channels where cross regulator structures were not available, and 60 numbers of weather stations were there to identify the local weather networks and the soil moisture at that particular area. And one flow meter laboratory was also a part of the scope. This was a project region spread across 5 channels, 5 canals. As you can see the color distinction here, this being Narayanpur left bank canals, main offtake distribution area, command area. This being the Shahpur branch canal, which is SBC. The small yellow color region was the MBC, Mudbal branch canal. This green part was JBC, Jewargi branch canal. And finally, the lengthiest one of 176 kilometers in length itself, the canal is called Indi branch canal. And this was a command area of 408,000 hectares approximately. And now the whole thing was operated with the star mark, which is blinking right now on the screen. So this particular command center was able to control each and every gate which is there in the network. That is around 4,500, approximately 4,500 and gates, 500 gates from this particular small location. All the gates were ArcGIS, and they were marked with the respect to coordinates and then put to the GIS platform for the management and feeding into the software. Now, this is a small illustration like how exactly the whole transformation looked like. The initial structure appeared like this, a small vent with no control structure. This is a field channel directly going to the field of a farmer. Now you can see that a small bund was created by the farmer, who are intelligent enough to identify that if there is head, there will be submergence to my channel, and then only I will be getting the water. Now, this particular structure was demolished or excavated, and a new structure was formed, and the gate was installed. Gate was then provided with the pedestal and the solar panel on its own, and the radio communication setup, which is now ready to talk to the gate and the towers around. Now you can see that the bund has been completely removed, and you can see the smoothness of the water which is flowing through it thanks to the modernization that was done in this particular area. Another example of the distributive optics where the gates were, the twin gates were there, and then you can see the height of it. This is one of the largest vents, that is 1500 gates were established, where the vent size is 1500, and you can see that each gate has its own individual pedestal and is able to communicate with the central server about the water which is reaching there, how much water is there in the downstream, and how much has to be released and allocated to the downstream levels. Coming to the next scope of it was refurbishment of the existing cross regulators. You can see existing cross regulators. This is a refurbished structure where the existing gates, which were initially were leaking or damaged or in a very bad condition, were completely removed and replaced, and were sandblasted and zinc coated and put back into the channel. Then the side plates were undertaken through the same process, and but you can see that there is no significant change in the existing structure except where there is a strengthening that is required was introduced. And finally, the gearbox or the hoist mechanism was completely replaced. The conventional ones were quite heavy for operation, and then they were replaced with the new hoist mechanism. And this is how the hoist looked. And there was a RTU room that was provided, which is again enabled by the solar power of its own with the help of the solar panels, and they can be, um, operated from here only without any wired network. So these are all wireless operations. Here we have, in this project, we have used radio frequency to talk to the towers in between and the different structures and gates spread across the area. So dedicated RTUs are provided for each cross regulator site, and it has its own dedicated independent solar setup, and the tower is located at the lowest vicinity is allowed to talk to the RTU or remote terminal unit. And also to integrate and identify the flow which is passing through this structure, water level sensors were installed in the upstream and downstream, which measure the water which is flowing through them and is able to accurately measure the water flowing through the structure with an accuracy of plus or minus 5% of the actual flow. Going forward, you can see this particular existing cross regulator setup. This earlier version had completely refurbished one where the existing gates were completely refurbished and reinstalled. Here you can see that 3 of the 5 gates where the vertical gates were initially there were completely removed, and the flume gates were installed, the new gates were installed, considering that the operations based on the 3 gates are sufficient enough to maintain or regulate the flow. At the same time, the other 2 gates were also brought into the system and, are operating online as a single site. So there is a integration between the old technology and the new technology, and this is a structure at JBC 44.3 kilometers, and you can see the massiveness of the structures. And as I said earlier, there is minimal intervention with the existing civil structures. The existing piers were used, and then the necessary small minor modifications were done, and the gates were slipped through with the help of a single crane. Coming back to the communication network for remote and autonomous operations, the whole project spread over 450,000 hectares or 408,000 hectares was distributed with 15 towers independently spread, uniquely spread over their locations, and also has a redundancy with the help of the GSM network connectivity. Also, they are operational on radio frequency with two different bands. One is free band, one is ultra high frequency band, which is again licensed by the Department of Telecommunication, Wireless and Planning Commission. Each tower is 35 meters tall, and they operate on line of sight scenario of communication, and that happens by watching over each tower without any intervention in between. Going forward, each tower is again coming with its own solar powered network system, where it is independent of the power supply in the remotest of the remotest of the reach of the canal. And as small as 20 meters tower was installed on the building itself. You can just imagine the weight of the tower, which is around 200 kgs max, that is equivalent to three people standing on the roof. Now, a new cross-regulator structure. The question remains, like, how are we constructing the new cross-regulator structure? There were 45 new gates that were introduced into the cross-regulators, where at 20 different locations. Initially, the canal looked like this, no structure at all. The same thing was identified with the Hecker study, that there are gates in the upstream which are lacking submergence because of the uh, non-contingent pool that is not getting created at this particular level during the Varavani period. As a result, that particular place was excavated, a new structure was formed, and this is how the new structure now looks like. There is no additional room or anything is required here. The only thing is these gates have their RTUs as small as these, and they are again operated by solar panels, and are able to operate on their own, and they keep communicating with the main control center on a very regular basis. So all these new cross regulators are again solar powered, remote operational, and they have sophisticated technology and are built to have minimal manual intervention, and to implement the total channel control of contiguous pools, so that the submergence is created to the non-submergent gates and the water reaches the tail end of the distributary or the offtake. The central command center was established in the building of Krishna Bhagyachala Nigam Limited, and it is there at Bigudi at the star mark which we saw in the map, which was blinking, and you can see the control screens and the data operators who are operating the gates as per the instructions delivered from the field. Also, there is a training hall for the purpose of training of the farmers as well as the engineers, and the command center has dedicated servers and a battery backup, along with its own power generator, the diesel generator, for the purpose of maintenance of the power at this location. Last but not least, we have the weather stations installed at around 60 different locations. The 60 numbers of the weather stations are installed across the 450,000 hectares of land to identify or to accumulate the data at microclimatic conditions and microclimatic level. And sophisticated structures have their, they can be mounted on a single gate which is already existing, and that becomes a power source of the weather station itself. And the same data can be historically populated, and the data storage is available as long as we want in the servers. And these are again solar operated, and require least intervention of any manual observation. And these are the trends which you can see can be obtained from the weather stations, which can be seen like how much water, how much rainfall has been experienced on what date, and what was the wind speed, what was the small moisture at that particular region, so on and so forth. Now, why it is called a successful implementation of automation here? The first one, addressing the challenges. Let us see the challenges which we established earlier, whether they are addressed or not. The first one being farmers and engineers training is the first practice which was taken up. The training, whenever we introduce a equipment, it becomes a very integral part of the whole scenario, that you train the people or the stakeholders who are actually using it. So the first thing that was taken up was farmers and engineers training. The training to the beneficiary was the first step. The second step being water management protocol. A water management protocol was implemented or discussed with the team of engineers and the stakeholders of the irrigation department, such that the hierarchy is mentioned, like which subdivision or division or what level of management will be operating which level of gate, and who shall be sending the command to the gate at what level. Third one is demand collection from the government authorities. This is done for the scheduling part of it, if you remember, and the planning and protocols must be considered for releasing of the allocated share, which is there in the account of the stakeholder. And finally, the operations in the field. This is nothing but a well-planned structure of point number one, point number two, and point number three. That is proper training, understanding the hierarchy, and finally demand collection and then implementation. That is the operations in the field. And finally, the implementation of total channel control in contiguous pools has been marking as one of the many successes that the project has achieved in this region. So some photos from how farmer trainings were introduced, and here, the water user cooperative societies are wherever are available have been pulled in and talked about, because it is ultimately their own uh, property, and the best it works, the more beneficial it is. And the people in and around the region are now understanding about what this technology means to them by seeing the benefits which are already being delivered at their field level footsteps. So the water level management was done by setting up the hierarchy, that is, which engineer will be controlling which particular authorized operations for the offtakes, for the distributory sublaterals, and DPOs are usually the field channels, or DPs, which we call in certain places. That is DPO stands for direct piping outlets. So these are the gates which are directly operated, directly introducing the water to the field channels. And the finally we have this demand collection from the government authorities, and toll-free numbers were also distributed during the training sessions and implementation of the protocols, which resulted in a huge benefit of non-dependability on the certain static work stuff. Now, one more good thing that happened here was that when the engineering level was, given the authorities, they had to have the power of authority to implement that particular water level, which is flowing through that particular channel. So there is no mismatch or overlapping of the decisions which are coming through as a part of the policy point of view. Going forward, the operations in the field were done as in the smartphone pattern. These gates are there with the farmers and the you know the engineers over there who can clearly see the water which is flowing through them, the summary of the things which are happening, and if there is any alarm over there, even that can be monitored. These are the gate healths. We just saw the gate, and the health can be monitored remotely too, as well as from the SCADA control center. And the same thing can be done with the gate positions as well as flow modes, which are implemented